Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about development of lateral surfaces of the solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now here we have been provided with frustum of a square pyramid which is having edge of its base as 50 mm side. The base has been marked as A1, B1, C1 and D1 over here. Now, the top face of this frustum of the square pyramid happens to be a square with edge length is equal to 25 mm. So, on the top surface, we have obtained the points A, B, C, D and the edge length of the square top face of the frustum of the square pyramid happens to be 25 mm. Now we can see height of the axis of this frustum of the square pyramid. It happens to be 75 mm. So this way we have been able to obtain frustum of the square pyramid, and now we need to join A with A1, B with B1, C with C1 and the D with D1 over here. So these are four slant generators of this frustum of the square pyramid. Now we are required to obtain the orthographic front view and top view projections of the frustum of the square pyramid when one of the sides of the base, it happens to be parallel to the vertical plane. So this will be the appropriate orientation of the base of the square pyramid with respect to the vertical plane. So when the square pyramid is going to rest onto its base on the horizontal plane, so one edge or the side of the base will be parallel to the vertical plane over here, and the axis of this frustum of the square pyramid, it will be perpendicular to the horizontal plane. So now we are required to obtain the development of the lateral surface of the frustum of the square pyramid, and we have to show onto that development a straight line or a string which is going to join two opposite edges of this frustum of the square pyramid over here. So one of the edge will be lying onto the top face, another edge it is going to lie onto the base of this frustum of the square pyramid. Now we are required to join the midpoint of one of the edges of the top face and the midpoint of the opposite edge of the base over here. So this string we are required to obtain onto the developed surface, and we are required to obtain thereafter the projections of this particular string into the front view projections and the top view projections over here. So we can check it out. This is the projection of the base of the square pyramid onto the ground having edge length is equal to 50 mm. Now this is the top view corresponding to the top face of the frustum of the square pyramid having edge length is equal to 25 mm. Now if we are going to look from the top view over here, so this midpoint onto the edge CD of the top face, this we are going to label as point P, whereas another point which will be lying onto the base end which is opposite to this edge of the top face, this point will be point Q. So into the developed surface we are going to join these 2 points P and Q over here, and then into the front view and the top view projections we have to obtain the projections of this particular string into the top view and the front view projections over here. So now let us begin with evaluation of the top view projections of the frustum of the square pyramid. So we know that one edge of the base happens to be parallel to the vertical plane having edge length is equal to 50 mm. So let us draw the top view projections corresponding to the base of the square pyramid over here. So edge length is 50 mm. Now we have obtained the points A1, B1, C1 and D1 into the top view projections over here. We have assumed that this edge C1, D1 will be parallel to the vertical plane. So now we have marked these points A1, B1, C1 and D1 corresponding to the base of the frustum of the square pyramid onto the horizontal plane. Now we can join the diagonals B1, D1 and A1, C1 over here, so that we'll be able to locate the access point corresponding to this frustum of the square pyramid. And we also know that on the top face, the edges AB, BC, CD and DA, they are also going to measure 25 millimeter each. So corresponding to the top face, we have obtained the projections of the top face points A, B, C, D into the top view projections over here, such that the distance between each one of these points, it will be equal to 25 millimeter. And now we can join the slant edges AA1, BB1, CC1 and DD1 into the top view projections, because these slant edges, they will be visible to the observer as the observer is going to look at this frustum of the square pyramid from the top view projections over here. So this way we have been able to obtain the top view orthographic projections of this frustum of the square pyramid over here. So now we need to obtain the front view projections of the frustum of the square pyramid. So we know that the height of the frustum of the square pyramid happens to be 75 millimeter. Now we need to draw projectors from all of the points of the top view into the front view projections over here. So once we mark the access height is equal to 75 millimeter, so we know that corresponding to the top face A, B, C, D of the frustum of the square pyramid. So once we draw projectors from A and D and B and C into the front view projections, so at a height of 75 millimeter, we are going to obtain a horizontal line projections into the top face projections of this square pyramid over here. So points A and D, they will be projected as A dash and D dash into the front view projections at a height of 75 millimeter from the XY reference line. Similarly, points B and C, they will be projected as B dash and C dash onto the top face projections of the frustum of the square pyramid at a height of 75 millimeter from the XY reference line. Similarly, corresponding to the base points A1 and D1, we have obtained the points A1 dash and D1 dash onto the XY reference line. Similarly, corresponding to the points B1 and C1 of the base of the square pyramid, we have obtained the front view elevation projection points as B1 dash and C1 dash onto the XY reference line. And now we can join A dash, A1 dash and D dash, D1 dash in the front view projections over here. Similarly, we have joined B dash, B1 dash and C1, C1 dash over here. So one thing here we need to remember, that the projections corresponding to the slant edges, that is D1 in the front view projections, it should be drawn as a dotted line or a hidden line projections, because this slant edge happens to lie on the rear side, but this slant edge DD1 has been overlapped by the front face slant edge AA1 over here. So therefore the dotted line projections corresponding to D dash, D1 dash, they have been covered by object line projections corresponding to the front side slant edge A dash, A1 dash over here. Similarly, the slant edge CC1 also lies at the back side. So we should have obtained the dotted line projections corresponding to the front view projections of the slant edge C dash, C1 dash. But these dotted line projections corresponding to C dash, C1 dash, they have been covered by or they have been superimposed by the object line projections corresponding to the front face slant edge B dash B1 dash over here. So that is why we are not able to see any hidden line projections into the front view projection over here. So now we have been able to obtain the front view as well as the top view projections corresponding to the frustum of the square pyramid. In order to obtain the development of the frustum of the square pyramid, we need to obtain the complete pyramid over here without any truncation. So what we have to do? We have to extend the slant edges A dash A1 dash and D dash D1 dash over here till it intersects with the axis point. Similarly, we will be extending the slant edges B dash B1 dash and C dash C1 dash till it intersects with the axis point. So the apex point corresponding to this frustum of the square pyramid has been obtained. Once we obtain the apex point, now we can see the slant edges of the original square pyramid, that is O dash A1 dash, O dash D1 dash, O dash B1 dash, O dash C1 dash. All these four slant edges, they happen to be inclined with respect to the horizontal plane. Similarly, into the top view, OA1, OB1, OC1 and OD1 slant edges, they are also inclined with respect to the vertical plane. So all these slant edges in the front view as well as in the top view, they will be inclined with respect to the two reference planes, that is horizontal plane and the vertical plane. So the true length of the slant edge is not available with us either in the front view projections or in the top view projections. So what we have to do now? Now we need to obtain the true length of the slant edge into the front view projections over here. So how that can be done? Through point O and O1, we have drawn a horizontal projector line. Now all these four slant edges, they will be equal. So this thing we know. So now any one of the slant edge we can pick up. So here we have picked up the slant edge OB1 over here. So this slant edge OB1, it is inclined with respect to VP in the top view projections. This slant edge O dash B1 dash, it also happens to be inclined with respect to HP in the front view projections over here. So using the principle of rotation of the line, what we are going to do? With O as the needle point, will open compass is equal to OB1, and this apparent length in the plan we are going to rotate so as to make this apparent length parallel to the vertical plane. Now we have been able to obtain the transformed apparent length of this slant edge as OB11. Now through this point B11, when we drop perpendicular projector into the front view projections over here onto the locus line corresponding to the point B1 dash over here, wherever this vertical projector drawn through the point B11 will be intersecting with horizontal locus line drawn through the point B1 dash, we will be obtaining the true length point corresponding to the point B1, that is B11 dash in the front view projections over here. And once we join O dash B11 dash over here into the front view elevation projections, now we have been able to obtain the true length of the slant edge of the square pyramid over here. Now once we have obtained the true length of the slant edge of the square pyramid, now with this radius that is equal to O dash B11 dash, we are going to draw an arc with O point as the center over here. This is point O. So with point O as the center, will open radius is equal to O dash B11 dash. And now we'll draw a long arc over here onto this arc. Now we are going to measure the edge length of the base. The edge length of the base will be 50 millimeter. So now 4 segments corresponding to the base we are going to obtain over here. So we have drawn 1, 2, 3, 4 arcs over here. So we'll start from point A11. then B11 will be there, then C11 will be there, then D11 and then A11 points will be marked alongside this arc which has been drawn with a radius of O dash B11 dash, that is the true length of the slant edge corresponding to this particular square pyramid, and the distances between A11, B11 and all the other points, they will be equal to 50 millimeter, that is equal to the true length of the edge of the base over here. So this way we have been able to mark 4 segments corresponding to the base onto the development of the square pyramid over here. So now the slant edges also we can join. So these are all true length of the slant edges which we have joined through the point A over here. Similarly, since it is the frustum of the square pyramid, so now we can check. Here we have got the apparent length corresponding to the slant edges over here. So this is the apparent length starting from O dash up to B dash C dash over here. So now this apparent length, now we have to transfer it onto the true length over here. So we can check. We have transferred all these 4 points A dash, B dash, C dash, D dash onto the true length. So this point name will be A1 dash, B1 dash, C1 dash and D1 dash over here. So this point will represent A1 dash, B1 dash, C1 dash and D1 dash. Now with radius is equal to O dash, A1 dash, B1 dash, C1 dash and D1 dash, another arc has been drawn over here corresponding to the top face of the frustum of the square pyramid. Now this edge length happens to be 25 millimeter. So now the edge length 25, 4 segments we are going to obtain over here corresponding to the points A1, B1, C1 and D1 and A1 over here. Now we have been able to obtain the development of the frustum of the square pyramid once we join the remainder slant edges over here, that is A1, A11 has been joined, B1, B11 has been joined, C1 has been joined with C11, D1 and D11 have been joined, and similarly A1 and A11 have been joined. Now we have been provided with the information that midpoint of the edge CD has to be joined with midpoint of the opposite edge of the base A1, B1 over here using a string over here. So we'll obtain the midpoint of the C1, D1 as point P. Now opposite edge happens to be A1, B1. So A11, B1 lies over here. This is A11. This is B11. This is measuring 50 millimeter. So the midpoint 25 millimeter, point Q will be located over here. So now onto the development, we are required to join points P and Q over here. So once we join points P and Q onto the developed surface using a string over here, and this string, once we join the points P and Q into the developed surface area, now this string has intersected with the slant edges C1, C11 and B1 and B11 at the points R and S respectively. So point R happens to be the point of intersection of the string PQ with the slant edge C1, C11. Point S happens to be the point of intersection of the string with slant edge B1 and B11. Now let us locate these 4 points P, Q, R, S into the front view and the top view projections over here. So now if we bring point P in the reverse direction, if we just try to project point P in the reverse direction, we find that point P happens to lie at the midpoint of the edge C1, D1 over here. So if we bring it back, so we find that this is the point on the true length, this will be the point onto the apparent length, and between C dash and D dash, we will be able to locate the point P dash in the front view. Now, if we bring this projector from P dash in the top view projections, so we'll find that point P dash was lying onto the edge C dash, D dash in the front view projection. So once we bring a projector from P dash into the top view projections, so this point will be projected over here at the midpoint between the points C and D in the top view projections over here. So point P top view has been obtained into the plan projection view over here. So one point we have located in the elevation view and the plan projection view. So this point happens to be point P. Now next point which is available with us, it is point Q. It is lying onto the base between the edges A1 and B1 over here. We can see over here. So once we look at this model also, we'll find that point Q happens to lie onto the midpoint of the base edge A1 B1. So into the true length lateral surface development over here, Q was lying between A11 and B11 at the midpoint. So if we project it back, so we find that into the apparent shape projections, that is the front view projections over here, the point Q dash will be lying at the midpoint of the base edge A1 dash and B1 dash over here. We can check this point happens to be A1 dash, this point happens to be B1 dash. So at the midpoint of A1 dash and B1 dash, we have located the point Q dash over here in the front view projection. Now if we bring a projector through Q dash into the top view projections, we will find that onto the base edge A1 B1, the point Q dash will be projected as point Q over here. So point Q will lie at the midpoint of the base edge A1 B1 in the top view projection. So point P has been located, point Q has been located in the top view projections, as well as P dash and Q dash, they have also been located in the front view projections over here. Now the next point which is available with us, it is point R. So now how we can project this point R back into the elevation projection view? So we know this true length of the radius OR over here. So onto the true length of the radius OR, we'll open the compass is equal to OR, bring it back onto the true length projector corresponding to the slant edge over here. Now this point R has been transferred onto the edge O dash A11 dash over here. Now once we bring this point over here, that is point R is obtained over here. Now using a straight line projection, horizontal line projection over here, this point R will be projected back to this slant edge in the front view projections over here. Which is this slant edge? C1 C11. So in the front view, where this will be lying, this is C dash and C1 dash. That is from this point, a horizontal projector corresponding to point R will be projected onto the slant edge C dash and C1 dash into the front view projection, that is onto the apparent length projections corresponding to the slant edge, that is C dash and C1 dash. So this point will be located as point R dash. So this is the apparent length which is available with us, and this is the location of the point R dash. Now we know that point R dash happens to lie onto the slant edge C dash and C1 dash. Now this point we need to locate into the top view projections onto this slant edge C1. We can check the corresponding top view projection of this slant edge happens to be C1. So now from point R1 dash, if we bring a projector in the downward direction into the plan projection view, so wherever this projector from R dash, it is going to intersect with the top view projection corresponding to the slant edge C1. So we will be obtaining the point R into the top view projection over here. This is the location of the point R, which is obtained onto the slant generator C1 over here. So this way point R has been located into the front view projections as well as into the top view projections over here onto the slant edge C dash C1 dash in the front view. CC1 into the top view projections over here. And the fourth point which is available with us, it is point S. So once again, we know that onto the true length of the slant generator, the true location of the point S has been obtained over here. Now again, with O as the center, radius is equal to OS. We'll open the arc again, mark this point S or transfer this point S onto the true length over here. So from the true length, I have to project this point back horizontally onto which projector line? Onto the projector line B1 and B11, that is B dash and B1 dash over here into the elevation projection view. So now since the point S, it happens to lie onto the true length B1, B11. So now from this point which is obtained onto the true length, again a horizontal projector will be drawn onto the slant generator B dash, B1 dash over here. So now the intersection of this horizontal generator with the slant generator B dash, B1 dash, it will provide us with the location of the point S dash over here. So this point happens to be S dash in the front view projections over here. So now this point S dash happens to lie onto slant generator B dash, B1 dash. So where does BB1 lie in the top view projection? So the corresponding slant generator in the top view has been represented as BB1. So from this point S dash, now once we bring a vertical projector in the plan projection view, wherever this vertical projector emerging from S dash will be intersecting with slant generator BB1 in the top view projections over here, point S will be located into the top view projections over here. So this way, all the 4 points P, Q, R, S, they have been located into the front view projections and they have been located into the top view projections over here. So let us join each one of these points. So into the top view projections, the line joining P with R, R with S and S with Q, it will be visible to the observer as an object line, because from the top, all these elements of the string, they will be visible to the observer. But when the observer is going to look from this side, so string QS will be visible, we can check. So we have joined the string QS with an object line, that is Q dash S dash in the front view projection as an object line. SR will be visible because it is lying onto the boundary. So R dash S dash has been joined in the elevation projection view as an object line because it is falling onto the boundary of this frustum of the square pyramid over here. But this portion of the string PR, it is lying onto the back side as the observer is going to look at the solid from this side. So PR string in the front view projections, that is P dash R dash portion of the string, it will not be visible to the observer. So that is why P dash R dash has been joined using a dotted line. So now we have been able to obtain the shortest distance between the midpoints of the opposite edges on the frustum of the square pyramid, where one of the edge, it is lying on the top face of the frustum of the square pyramid, whereas the other edge whose midpoint needs to be joined, it is lying onto the base of the frustum of the square pyramid. So onto the development, we have obtained a straight line linkage between these 2 points P and Q over here, which are going to lie on the opposite edges of the top face and the base of this particular frustum of the square pyramid. And the location of all the points lying onto the string which is going to join the points PQ, we have obtained into the front view projections and the top view projections as well. So this is all for today. So I hope that through this discussion you would have learnt about the procedure to obtain the development of the frustum of the square pyramid to begin with, and also you would have learnt about how do we obtain the shortest distance between 2 points which are lying onto the opposite faces of the frustum of the square pyramid, when one of the edges it is lying onto the top and another edge it is lying onto the base of the frustum of the square pyramid over here. So this is all for today. So we are going to continue with further discussion regarding few more illustrative cases of development of surfaces of the solids in the coming lecture sessions. So thank you very much. Thanks a lot.